So, good evening. Good evening, everyone. My name is Rachel Barron. I'm the Executive Dean of the Faculty of Natural, Mathematical and Engineering Sciences, and it's a real pleasure to welcome you here this evening. Those of you from within the faculty or within King's, and those of you from outside. Real pleasure to invite you and welcome you. So, I had in my invite to this event that it was the Physics Inaugural Lectures Series. And I said, but the head of engineering is coming. And I was like, what's happening here? But of course, Chris is being welcomed back into the fold of physics this evening, and having spent many years in physics. And I also thought, well, that's a good thing, because we are the Faculty of Natural, Mathematical and Engineering Sciences with a real commitment to interdisciplinary science. And so what a great example of where we can work across those disciplinary boundaries. And I'm really excited to hear the talks today. So the first talk we're going to have is from Professor Alexandre. I didn't quite get all my homework done to find out when he was made a professor at King's, but he can't remember either, so that's fine. We think it's about 3 or 4 years ago, but we're delighted to have your professorial inaugural lecture tonight. Just a little bit of background information. So Jean undertook undergraduate studies, masters at École Normale Supérieure de Lyon in France, and then went to study for his PhD at the Louis Pasteur University of Strasbourg. First postdoc was on an interesting topic called the finite temperature phase transitions in particle physics, and that was based in Athens. And then he joined King's. 2001, he joined King's, firstly as a Leverhulme Trust postdoc, and then joining as a lecturer. Now, Jean is in the research group of theoretical particle physics and cosmology. And I was trying to think if I could make some comments about how the talks are connected to today. We have two slightly different research themes. And the first theme I thought of is actually the first thing Jean mentioned to me, which was beer. I'm like, right, okay, I'm sure enough said about that one. The other theme, though, is about, well, what is it about physics? What are some of the themes of physics? And to me, you know, as a mathematician, but someone who enjoys and admires physics greatly, there's an aspect about trying to understand the fundamental nature of materials, of stuff. You know, what is the nature of stuff? And we'll hear a little bit more about the nature of stuff that Chris works on, which is perhaps a little closer to my area, looking at molecular and atomistic scale simulations of stuff. But I also think that work of theoretical physics is about really understanding, you know, the hard stuff, quantum field theory, symmetry violations, the real nature of particles. So I'm really excited to hear more about your journey, Jean, and your research. And I welcome John to the stage now.
Let's see. Okay, I can click, actually. Hello, thank you for turning up. It's very nice to see people here. So, about 10 years ago, the most powerful particle accelerator on the planet was upgraded, the Large Hadron Collider at CERN. And there were fears that some black holes could be produced and swallow the Earth. So this hasn't happened, fortunately, but is it still a worry, potentially, for the next generations of particle accelerators, even more powerful? Well, I will try to answer this question from what I understand. I don't understand much, but I will give you some ideas. So let's start. For those who came here just for the drinks, the summary is, don't worry. So let's start with a very simple concept. So in classical physics, a particle follows a specific trajectory, and given the initial conditions and given the forces which induce this motion, we know exactly where the particle will end. We know where this particle starts, it goes. We know which slit it will go through. We can predict where it arrives. So in quantum mechanics, it's a bit different. If you emit an electron here on the left and you observe it somewhere on the right on the screen, you don't know which slit it went through. And this is not a problem of precision of the experiment. It's a fundamental uncertainty, which cannot be explained by classical physics. So what is the transition between quantum and classical physics? So in general, this is a very difficult question, but in this specific setting, it can be understood as follows. You consider the de Broglie wavelength of the electron, which is the inverse of its momentum, and you compare this length to the size of the slits, and the distance between the slits, and you can tell roughly in which regime you are. So for a relativistic electron moving very quickly, this wavelength is quite short compared to the slits, and the electron can be considered classical. You can define the trajectory. But for slow-moving electrons, this de Broglie wavelength increases, and when it comes comparable to the slit, the size of the slits, then it's the quantum aspect which has to be taken into account. So this tells roughly in which regime you are. So if you do this experiment with many electrons, you start to build up an interference pattern on the screen, which is similar to what you would get with light. And this shows that particles and waves share common properties, leading to what we call particle-wave duality. And so how can what formalism can allow us to describe this duality? So this is a quantum field theory. This is my worst slide. I didn't know what else to do. So a field is everywhere in space and in time. It's all around us. And it can create particles which are interpreted as excitations of this field above its ground state. So as a very, very basic, very rough analogy, if you can imagine a pond with water, so the field is the water. It's a very bad analogy, but the field is the water. The ground state is a still surface, and particles correspond to ripples on this surface. It's very, very roughly this. Slightly more formally, a field is a big matrix, an infinite matrix, with a continuous set of rows and columns, which acts on an infinite vector with a continuous set of components to give, on one given state, to give another state. So it's basically linear algebra. This is also very rough. Then there are different regimes in quantum field theory. There's a perturbative and non-perturbative regime. So if I come back to this analogy with ripples on a pond, perturbative QFT corresponds to very small ripples, small compared to the size of the pond, and non-perturbative regime corresponds to bigger ripples which overlap in a nonlinear way. Okay, very roughly it's this. And so since the early days of my research career, I was dealing with non-perturbative aspects of field theory, of quantum field theory. So in France, in doing my PhD, I studied a beautiful approach to quantum field theory, which is exact Wilsonian renormalization equations. Fantastic. This explains how the description of a system evolves when you change the scale of observation. So if you have a system that you study, you zoom out, and this approach tells you how the degrees of freedom and the parameters which describe the system, how they evolve as you zoom the system out. And this is I think it's a very deep interpretation of quantum field theory, because it really made me understand how quantum fluctuations build up in the system. I really developed some intuition about quantum field theory because of this approach. At the end of my PhD, I decided to go for an adventure, and I decided to go for a postdoc in Greece, in Athens. So I bought a small car, a small, cheap, second-hand car, Twingo. I put my physics books, I took my swimming shorts, my toothbrush, and wow, I went to Greece for 2 years. It was an amazing experience. I arrived there, I couldn't believe the weather. The weather is unbelievable. The food is outstanding. I discovered a new culture, a new way, lifestyle. I learned a new language. It was really amazing. These 2 years were, wow. Well, I did a bit of physics too, because it was a postdoc after all, not only a holiday. And I studied there, I worked on non-perturbative aspects of quantum electrodynamics in the presence of an environment. So it was temperature and magnetic field. So this has it happens that there are very interesting non-perturbative properties in quantum electrodynamics in the presence of a strong magnetic field. So I was looking at this. But overall, during these 5 years, so 3 years of PhD and 2 years for my first postdoc, these 5 years were very important for me to understand new concepts and to develop an intuitive approach to quantum field theory. Of course, I learned and I understood many more things after this, but these 5 years really determined my way of thinking about quantum field theory that I still use now during my research. Okay. So now let us come back to this particle wave duality. And this is my first important slide. I have 2 important slides only. So I'll let you know when the second comes so we can sleep in between if you want. But this is my first important slide. So quantum field theory is based on quantum mechanics and special relativity. So from the quantum mechanics point of view, a fundamental property is the uncertainty relation. So if delta x is the uncertainty on the position of a particle, and delta p the uncertainty on its momentum, the product of these uncertainties is of order 1 at least. And this, again, is not related to a lack of precision of some experiment. It's a fundamental uncertainty, which cannot be explained by classical physics. Now, from the relativity point of view, a fundamental feature is the equivalence between energy and mass, or momentum and mass. And from this, if you consider a single particle, a single free particle, the uncertainty on its momentum must be so smaller than its mass, otherwise you would create other particles. So if you put these 2 together, you find that the uncertainty on the position is at least of order 1 over m, which is called the Compton wavelength. So in the standard model of particle physics, a fundamental particle is mathematically a point. So with no dimension, 0 length, there's no radius. It's not a ball with a radius. It's just a point. But physically, a particle is more like a fuzzy object with a typical spatial extension of the order 1 over its mass of this Compton wavelength. This is how you can think of a particle. And I will come back to this in a few slides. So for the electron, for example, this Compton wavelength is of order 10 to the minus 12 meters. So this is 0 point, there are 11 zeros and 1 meters. So is this small or what? Actually, so you need to compare this to something else. And actually, this is about 100 times smaller than a typical atom size. So it is kind of small, but it is not 0. There is a certain extension which defines this fuzzy object. This was the first important slide. So before coming back to this, let's tell a bit more about relativity. So if 2 observers move away from each other, but they study the same system, they will measure different lengths and different times. But there is a very important principle in physics, which is a democratic principle, is that all the observers will use the same equations to study a given system. And as a consequence of this, there's a specific symmetry between space and time. It's called Lorenz symmetry. It's not Chris Lorenz. It's Hendrik Lorenz, few generations before, unless there is some connection, but the spelling is different. Yes. So this symmetry is really fundamental at special relativity. And if you make this symmetry local, so depending on the space the point where you are in space, you end up describing gravity in terms of geometry. So geometry where space-time is curved, so matter tells space-time how to curve, and simultaneously, space-time curvature tells matter how to move. It's very, very roughly, it's this. So I started to introduce gravity, a bit of gravity in my research when I came to England. I was a bit shocked by the weather after 2 years in Greece, you can imagine. But then, fortunately, I discovered English relays. And this was a new dimension. So since I arrived in England, I studied in different collaborations, different topics involving QFT and a bit of gravity. But a main collaborator in all these years was Nick Mavromatos, who has come from Athens for this evening. I'm very happy about this, because Nick has played an important role in different stages of my career. So, and if I'm giving a talk now, it's partly because of him. So thank you, Nick. So part of my work, it was just at some point, for a few years, I was interested in a potential symmetry violation of this space-time symmetry. So I worked on this a bit. There was something very exciting at that time. Some big experiment had announced potential superluminal neutrinos. Oh, this was shocking for everyone. Shocking for those who expected that this would happen, like me, and shocking for those who couldn't believe that this would ever happen at these energies. But it was really, and all the community was expecting a confirmation of this, until this experiment found that some cable had not been plugged properly. So this was a disappointment for part of the community and a relief for another part of the community. Here again, if you make this symmetry violation local, you end up with something called a modified gravity, modified compared to the Einstein general relativity. I don't really know what to believe about these theories, but I think they are very creative and they're definitely worth studying. But let's come back to general relativity as defined by Einstein. So for the purpose of this presentation, I will give a very basic, very simple definition, okay, of black hole. So a static black hole is a spherical region in space somewhere, which is completely disconnected from the rest of the universe. So anything can fall in, but nothing can come out, even light. So a black hole is, if you want, is this region which is beyond a horizon that you can reach, but you can never come back from it. And so this horizon has a certain radius called the Schwarzschild radius, and the radius of this sphere, this region, is 2 gm. So m is the mass of the black hole, and g is some constant which defines the strength of gravity, or the weakness of gravity. So according to GR, to general relativity, the black hole, this sphere is empty inside, and the curvature increases as you go towards the center and becomes infinite when you are at the center. So these are mathematical properties, but apparently black holes are real astrophysical objects. So in this very famous picture here, what you can see is the synchrotron radiation emitted by some plasma around a supermassive black hole in some galaxy not far from here, just outside the M25. And what you can't see is, in the middle, is the black hole itself. So coming back to this Schwarzschild radius, you can define a Schwarzschild radius for any object. For me, it will be very small, but you can define a radius for any object. So for example, for the Earth has a radius of about 6,000 kilometers, and the corresponding Schwarzschild radius is about 1 centimeter. This means that if you wanted to create a black hole from the Earth, you would need to crush everything, to squash everything into a small ball like this. All the oceans, all the mountains, the cheese, all the beer, everything into a small ball like this. And then you would induce a black hole. So you can imagine which kind of density you need to reach in order to form a black hole. This also gives you a hint for the conclusion of my talk. The Sun is about 700,000 kilometers of the radius. The corresponding Schwarzschild radius is about 3 kilometers, which is very, very small compared to the Sun. So big stars, at the end of their life, when the nuclear reactions switch off, then they collapse under their own gravitational field, and under their own weight. And if they're big enough, they will collapse within this Schwarzschild radius and become a black hole. But this is not the case of the Sun. Okay, so now I think that's my second and last important slide. Yes. So now imagine you're in a collider, in a particle collider. In the center of mass frame, you have a beam coming and you collide and you create some particles. Some of them can be fundamental particles, others can be composite particles, but you create particles. So let's consider one of these particles which is created. So as I said before, this particle can be thought of as this fuzzy object with dimensions 1 over m, 1 over its mass. But if you want to create a black hole with this particle, all these fuzzy objects should be within its horizon, its Schwarzschild radius, which is Schwarzschild diameter, which is 4 gm. So one of the Compton wavelength should be smaller than the Schwarzschild radius, times 2. If you rearrange this, you find that m should be larger than 1 over 2 square root of g. 1 over square root of g is very, very famous. It's called the Planck mass. And it's huge, it's huge. The Planck mass is about 10 to the minus 8 kilogram. That's 0.0000001 kilogram. This is enormous, because this is 10 to the power 23 times the mass of the electron. It's insane, it's enormous. So how can you even think of this? And the Planck mass is also 10 to the power 15 times the maximum energy that you can create at the Large Hadron Collider. 15 orders of magnitude. It's a 1 with 15 zeros. It's insane. I mean, okay, we don't even know what gravity looks like at these energies. We don't know actually. Okay, there are many theories, but we don't. The reality is that we don't know. Also, we expect new physics in this whole range of energies, which has not been explored yet. But the discrepancy in the orders of magnitude is so large. Is it realistic to imagine that any collider could generate a black hole one day? I don't believe. But okay, maybe this is a personal point of view, but I think we are safe. I believe that it's okay. So after this, you can have drinks in peace. You don't need to worry while you have your drinks. So this is the conclusion of my talk, actually, for the scientific content. So there is something here. This argument I gave you is very simple, very naive. It's very hand-wavy. But I think it contains quite a lot in terms of intuition. And this is something that, as an undergraduate student, I was unable to have this kind of hand-wavy argument to understand what happens. Because I had a very formal and very mathematical education in France, and intuitive and hand-wavy arguments were looked down. I mean, it was so I think it was a very good education, but some intuition was missing. There was something that I needed to learn, to get some intuition here in England. Well, I had a lot of hair, actually. It was a hassle to wash. It's much easier now. But I thought that I wanted to become professor at this time already, but I never imagined that I would become a British professor. And here I am with my citizenship certificate at this official ceremony. I was expecting the Queen to turn up in person and give me my passport, but no, all I got was this glamorous picture. But in any case, this ceremony for me was very, very moving because I really love my life in England, and also I'm very proud to have completely lost my French accent.
Wow. That's not exaggerating.
Thank you.
So you have a double act here, but don't worry, it's not going to be twice as long to delay you from the drinks. Traditionally, it's the head of department that gives a vote of thanks. And of course, I'm absolutely delighted to thank Jean for merci, Evcharisto, for a wonderful, engaging talk, and the photographs were fantastic. But Professor Nick Mavromatos absolutely pleaded, he really wanted to give the real vote of thanks. So it's with great pleasure I introduce Nick Mavromatos to thank Jean.
First of all, I would like to thank Jean for insisting that I would do that. So he said that he never lost he is happy to lose his French accent. You never had a French accent, you had an Alsatian accent, which is a mixture between French and German, but that's all right. Well, I'm delighted for this occasion because really I know Jean when he was really young, let's say. A bit younger. I mean, he came here, as he said, as Professor Baman said as well, from Athens. I met him for the first time when he was in a conference in Strasbourg, where his professor of PhD Poloni was organizing. And then he was telling me that he's a postdoc in Athens, in the National Technical University. Actually, he was a Marie Curie fellow. That's the only thing he didn't say why he liked Greece, because he lived in Greece with the salary of the European Union. Because if you lived with the local salaries, you wouldn't have these memories. The people in National Technical University, they were delighted. In fact, right now, Farakos and Kouchoubas asked me to congratulate you on your occasion, and they are sorry that they cannot be with you, but he left fond memories from his stay. Then the real adventure came, because Shaban Sarkar, Simon Hans at Swansea, and myself at Oxford at the time had a triangular Leverhulme grant, and we were advertising for a postdoc for a second time. We had a first postdoc, and then he left, and we were advertising for a second time. And then Jean applied to do a project on high-temperature superconductors and gauge theories. He was already expert in gauge theories, as he explained to you, and we've been delighted that he's been here, and we produced first-class work there. But then Jean, during his postdoc, he volunteered also to teach. You know, those days, early-stage researchers volunteer. This is rare to teach. This is rare this time. It doesn't happen. But this paid off, because it led him to a lectureship, because the students loved him. In fact, despite the fact that there was a rule, a golden rule, like average mark times love of students equals constant, the students loved him even when he was marking very harsh. He had a French rigorous education, so you can imagine the marks. He was teaching mathematical physics. You can imagine the average marks and the level of... But the students loved him. Even if they failed, one of my students said, I'm going to pass the second time because I feel ashamed that I failed the first time. So that shows you the level of commitment that Jean had over the years, which he continued, even now as a professor. He did many other things, which he didn't say because of his modesty. For instance, he develops non-perturbative techniques for the metal experiment now to do, they are looking for exotic things, monopoles and other avatars of new physics. I am delighted that, as I said, and now I'm closing, I don't want to waste further of your time. I'm delighted that he made it as a professor. Of course, it's good for him. He's a professor in a very famous place, King's College, so his dream has been achieved. His second dream, because the first dream was to become British. And I think you became professor 5 years ago, if I'm not mistaken. It was just before the COVID, I believe. But I think so. Sorry? 2001. 2001? 21. Okay, 3 years only. Okay, fine. Never mind. Okay, but never mind. I'm delighted that I had this opportunity to present him to you, and I wish him all the best from now on. It could only go up from now on, scientifically. I'm pretty sure I wish you some of your conjectures in physics to be verified in gravity, and not to make a black hole, of course, within our premises. So thank you very much, Jean. All the best. And we thank you for being with us, and I hope you're enjoying it. Thank you.
So we now move on to our next speaker, who also is very well known to you all. So Chris, giving a little bit of the backstory again, studied at the University of Michigan for his undergraduate and PhD in chemical engineering then, looking at chemical engineering applications of percolation theory. Then in 2001, he started his first postdoc, first of all in the Multiscale Materials and Molecular Biology Simulations group at Sandia National Labs, and then on to Iowa State University in the physics department. He then joined King's in 2007 in the engineering division, as was, before joining the physics department in 2011. Now, I know he was a very valued colleague in physics, and I must admit, when I made one of my first appointments in the faculty, which engineering were thrilled about, having Chris as their head of department. I think one of the hardest things to do was wondering who in physics was going to kind of kill me first. Because, Chris has done amazing things in the physics department, as both in terms of his research, but also his contributions to the leadership team there. So, Chris, molecular and atomistic scale simulations. Very much looking forward to this, and maybe a slide with beer as well, if we're lucky.
Well, thank you so much, Rachel, for the very kind introduction, and thanks to the faculty and the department for inviting me to give this talk, even if I've kind of changed colors or whatever. But yeah, it's a great pleasure to do this. And so, I could have named my titles. There's going to be these themes that kind of come up. So I've had the opportunity to work with so many amazing people, and I'm very lucky that a lot of them are in this room today. And I think we've done some pretty cool stuff. And so that you're going to hear about a lot of people and the science we've done. I'm so lucky to have so many people who've supported me throughout this journey. And a lot of them are here as well. And they always say that we're standing on the shoulders of giants. And I feel like mine are just a bit taller than the average ones to help me out. And then just a philosophical question to keep in mind, is life cyclic or a periodic function? And I hope we don't get to a point where you're asking the last question. So I took the brief is telling you my path very literal, so get ready. This is going to be a tour de force. But I started out in Flushing, Michigan, which is the most typical of typical small towns in middle of America. You can see the population. We had one McDonald's, and that was the highlight, right? I was born into a family of of my dad and mom, who are both here, John and Alice Lorenz. They were both academics who rose to the top of leadership in their relative institutions, so they set a very high bar for what I need to achieve in order to surpass them at some point. And a lot of people ask me, so Chris, how did you end up being an academic? And for me, it was a process of elimination as much as anything else. So sports, didn't quite work out for me. Music, again, despite playing the trombone or whatever it is over there on the left side, not quite. Politics, I left that to felons. But then computational research, I found a very early, really high-tech computer I'm using there, and I thought that was my calling. So as Rachel said, my first step was to go to the University of Michigan, 45 minutes from my hometown in Flushing, and I spent a lot of time in that beautiful stadium there, which houses 120,000 people, double size of the town on football Saturdays. And in fact, American football played a really important role in my path to here. So it's all started at the Rose Bowl, January 1st, 1998, University of Michigan playing for the national title. We won, great celebrations. I'm there tailgating with my good friend, Chris Brown. He had come to study PhD in chemical engineering from MIT. And after all the celebrations died down, we looked at each other and we said, we're kind of deciding what to do. And he said, I'll stay and do my PhD if you do. And I said, all right, let's do it. I mean, there might have been some beers involved, but nonetheless. So I got on the plane back to Ann Arbor. I got off the airplane. I went and talked to Bob Ziff, who's here in the audience. And I said, Bob, I'm going to do a PhD. And he said, all right, quals, 4 days. Qualifying exams are in 4 days. Go get ready. I said, Bob, I just been in LA drinking and watching football. He's like, don't worry, just go do it. I think he did a lot of heavy lifting in the meeting afterwards where they assess whether they're going to pass people on quals or not. But whatever the case, I'm very lucky that he did. Then, as Rachel said, I studied percolation theory. Percolation theory is the simplest model that displays a phase transition, and I was on the numerical side. So I used Monte Carlo simulations to do simulations. And just to give you an idea of what percolation theory means, there's kind of two very classical models. One's called site percolation, and the other one's called bond percolation. And basically, you with some probability p, you occupy either a site or bond, and then you connect nearest neighbor, either sites or bonds that are connected, and you look at the connected sites, and those are what we call clusters. And then you can study the properties of these clusters as probability changes. And there's a very important value where the probability of p, where you have a cluster that spans in one dimension or another, and that's called the critical threshold. And then using Bob had come up with like some really clever algorithms that allowed us to do things just way better than anyone else in the field at the time. And so using that and my state-of-the-art high-performance computer, which was me jumping from desktop to desktop to desktop in undergrad computing lab and running simulations in the background, hoping some dedicated undergrad wouldn't come kill it and kill my research for the day. We studied a lot. We were able to calculate percolation thresholds to higher precision than anyone else in the field at the time. And I studied three-dimensional percolation, both on lattice and in continuum. Of course, Swiss cheese, because why not? I like food. So Swiss cheese model and a lot of other cool things. And, Bob guided me to have a very productive PhD, which laid the foundation for the next steps in my career. And from this point, I learned, the most important thing I learned is just how to mentor people. I mean, Bob was an amazing mentor for PhDs, and a lot of the ways I try to guide my own, or be mentors to my own students, are derived from things I learned from reflecting on how we work together. And one of the things that's most amazing is, as I said, he's here, and so it just reiterates it, is that mentorship doesn't end when you end your PhD. He's been there for every time anytime I needed him throughout my career, and it's amazing, and I'm so grateful and lucky to have had such a great supervisor. I also learned that Europe exists, because the first conference that Bob ever sent me to was a statistical mechanics conference in Paris, I mean, I don't hold it against them that the only place I ever went that was kind of even exciting after that was New Brunswick, New Jersey, where the hotel rooms had gunshot holes in them and all that kind of stuff. But nonetheless, I got to see Paris, and I got a passport, which is not exactly the most common thing in America. And I also learned that I quite enjoyed computational research, but if you look in some of our papers and you see equations like those in the corners, just know that that was Bob. I was the guy who did the numerics. Bob did the hard stuff, right? So that was my takeaway. And so after I got my PhD, then my first stop in my academic career after that was to move to Albuquerque, New Mexico, halfway across the country, you know, home of Breaking Bad, all that kind of stuff. And I had 4 great mentors there, Gary Grest, Mark Stevens, Mike Chandros, and Susan Rempe. And that's where I learned about molecular dynamics simulations, which is the wheelhouse of my research now. So molecular dynamics simulations allow us to study, as it says on the tin, the dynamics of molecules. And it's like a super high-powered microscope, so we can visualize what's happening. And I love this video because it looks like humans falling through the sky, right, as the molecules move. So I think that's really cool. But this is a real polymer. It's not just made up. It's real. It's not fake news, like someone once said. So, and just because I had to have a couple of equations, since I knew Jean was going to go first, and he was going to impress you with all of his really smart and hard physics. So, but molecular dynamics just uses Newton's second law of motion, F equals ma, and we calculate the force from what we call a potential energy. And the potential energy has terms that describe the interactions between molecules and within the same molecule. And then there's, you have to have a flow chart, because I'm in engineering now, so this is my flow chart. So you start with coordinates and velocities, you feed that into the simulations. The simulations calculate forces, update the positions and velocities of the particles, and it runs on computers for weeks, months, until you reach a state that you're happy, you want to study. And so at Sandia, I used molecular dynamics to study a variety of different problems, polymer fracture, nanotribology. We were the first ones to model the actual experimental setup, which is in Thomas force microscopy, which is this kind of tip, shearing on lubricated substrate, and then nano-confined liquids. And this experience then allowed me to realize that, you know, while Bob was an amazing mentor, he's not the only one out there. So, I mean, Gary and Mike and Mark and Susan were amazing. Gary still writes me emails every year to let me know how his football team did in comparison to my football team. And so that's always nice. That usually his team has done better than mine, so there you go. But I also learned there that collaboration is fun. I got the opportunity to work with postdocs and other scientists and realized that it was fun and a good way to do science. As I said, I learned what molecular dynamics were, and that's been important for me. I realized that having a proper supercomputer is a lot more efficient and a lot less exercise than going from desktop to desktop. But I applied to so many academic jobs while I was at Sandia and got rejected from every single one of them. And that's not so fun. And Gary Grest then one day just pulled me aside after 4.5 years. He said, Chris, just like at the end of Ferris Bueller, if you've seen the movie, they say, okay, it's time to go home now. He said, Chris, it's time for you to leave and go prove it that you can do the same stuff in academia in an academic setting. So I did that. So my next step was middle of nowhere in the middle of the United States called Ames, Iowa, at the Iowa State University. It was a great place to work, but it was no field of dreams for me. But I got to work with the great guy, Alex Travisit, there. And there I got to continue applying molecular dynamics to really cool problems, including things like self-assembly of polymer nanoparticles, and lipids and peptides interacting with lipids, which I've carried on in my own independent career here. But the coolest problem I got to work on there was a result of a PhD student, Josh Anderson, going to American Physical Society conference in Los Angeles, California, and coming back to me and said, Chris, they're running molecular dynamics simulations on PlayStations, and I want to do that. And I said, cool, let's do it. And just to get, so the point being is that because games are generated now with this very vivid graphics. Computers have to have what's called a graphical processing unit that's super high powered so that when you're trying to kill that alien, it doesn't lag or there's no disruption so the alien doesn't come kill you first when you thought you killed it. So, and these GPUs or graphic processing units are really good at doing fairly simple maths. And so, so Josh and I sat down and figured out how we could use these GPUs to run MD simulations. And Josh did all the hard work. He wrote all the code. I just kind of told him how MD algorithms work. So we wrote a code called HUMD. It was the first real large-scale computer molecular dynamics engine that ran on GPUs. And this is also significant because GPUs are more energy efficient and also more cost-effective than traditional computational hardware. And this work then, we wrote a paper which has been cited tons because of the popularity of our code, which is amazing for everyone involved. And for Josh, it turned into a career for him as he now went kind of full circle back to the University of Michigan. And he now works as a research software engineer, and as part of his job, he continues to develop and support HUMD. But of course, because it's now at Michigan, it's called HUMD Blue, but that's fine. So yeah, so that was a really cool project and something that, you know, has had a lot of legs. So that's awesome. So at Iowa State, I learned that I could successfully lead a research project by myself, which is obviously useful if I want to be a PI. That simulating biological molecules had a future. I didn't know I was going to win a Nobel Prize several years later, but yeah, that's cool. And that code development is fun, particularly if I don't have to do it myself. So then the first job I applied to after Iowa State was here at King's. The interview was on Thanksgiving Day. I thought that should be illegal, but I also thought I wanted a job. So I turned up, and I turned up. The job was being advertised to be in Mark Miodownik's group, the materials research group in engineering. And Mark did a postdoc at Sandia with Mike Chandros before I went there, so that's an important backstory. So I showed up for the interview. In those days, the interview was such that you sat in the same room with everyone you were competing over the 2 days of the interview. And I was sat there. Of course, I spoke to people. And I was the only simulation person there. Everyone else was experiment. And so I started thinking, did Mark invite me here as a favor to Mike? And I was like, nah, he wouldn't do that. So then the day the interviews went on, I walked down the hall for the proper interview part. And I asked Mark, I say, Mark, did you get my letters of reference? And he said, I don't even think we asked for them. And I was like, this is a favor. So I walked into the interview so relaxed. I was like, it's not going to matter, so let's just go for it. And at some point, the question was asked, Chris, why do you want to move to London? And I said, I really love football, meaning soccer, but I used the right word so I'd fit in, right? And I love good beer. And little did I know that there was a man named Jean Alexandre in my interview panel as the external interview person. And then I got to know Jean. Obviously, I got the job because I'm here. But I got to know Jean the years afterwards. And we were talking one day at the pub, as one does. And he said, Chris, do you remember the interview? I was like, yeah. He's like, when you said you like good beer, you had my vote. So, you know, drinking sometimes has positive ramifications, it turns out. So I arrived at King's on May 1st, 2007. Then I went to my first conference all the way across town at Imperial College a few months later. And there I met 3 people who I still collaborate with today. Jane Lorenz, who's here in the audience, Cecile Dreiss, who unfortunately is unwell and couldn't be here, and Richard Harvey, who's in Vienna. And I'm going to tell you more about some of the science we did in a minute. And I also recruited my first PhD student, Neil, who's here. And as anyone knows, is when they start out your career, it's so important. The first PhD student is a really important thing. And Neil was amazing. He worked on confined liquids. And then toward the end, we did some biophysics stuff, looking at how influenza peptides attack membranes. And that was with Franca Frattinelli, who's now at UCL and also is a great friend and someone I've collaborated with for quite a long time. And then an unfortunate incident happened, which is that in 2009, King's announced they're going to close the Division of Engineering. So as a young academic, that's not how you script it up. That, you know, you're going to start, and then 3 years later, they're going to tell you your department's going to end. But for me, it probably was a really great deal, because then somehow I was offered to join the Department of Physics. I think Mark did a lot, Mia Dovnik did a lot of heavy lifting in that case too. But anyway, nonetheless, and I was able to join this great collection of people here who were in the department and as part of the materials modeling group. And so I went from being the only simulation person in engineering at the time to being part of a community where, you know, not only me, but my students could learn and grow. So that was fantastic. And so I joined the physics department, and that's where my group really started to flourish. And one of the topics that we've been working on for as long as I can remember is self-assembly of soft matter. And so soft matter is material whose conformation structure can change at room temperature, whereas metals or solids can't, right? If you press on it, nothing happens at room temperature. And self-assembly is a process by which molecules, in this case, go from a disorganized state to an organized state due to some kind of specific interactions, but no external force acting on it. And this is where Cecile and Jane come into the picture, because they are experts in neutron scattering. We do molecular dynamics, and this are a really great complementary techniques for these kind of studies, because for our simulations, we need to know how many molecules are inside the aggregate, and they can measure directly how many molecules are in their aggregates they study. So that we have good crosstalk. Then we can both measure size and shape of the nanoparticles, so we can validate our simulations off of experiments. And then with the simulations, we can get all kind of detail about the molecular structure, internal structure, how self-assembly works, that's not approachable from this experimental thing. And also we can provide information necessary to help them model their experiments. And so we've studied a wide variety of different materials. Please don't, there's not going to be a quiz at the end, but I just wanted to highlight some of them. So we've looked at polymer nanoparticles to deliver therapeutics to membranes. And this is just one of the cool movies we can produce, so just a little eye candy real quick. We also studied nanoparticles made out of peptides that are kind of like viruses. So they're capsids like viruses, and trying to understand, we can make nanoparticles out of them to attack bacteria or whatever. We've looked at lipid nanoparticles, and we've looked at polymeric nanoparticles. We've also looked at cool processes like how lipid micelles are digested by enzymes in the body. We've looked at the encapsulation of drugs into surfactant micelles. We've looked at biosurfactants, and we've looked at conjugated polymers that are used for biosensing and biotherapeutics and stuff, and which is a really cool paper. All these things I could talk about for hours, but people would kill me, so I'm just not going to. Another great product of working with Jane was one day I walked in and she's like, Chris, I'd like to introduce you to another American. And that's Sylvia McLean, and I'm very grateful that she's here today as well. And Sylvia's from Tennessee, so not only does she have a more interesting accent, but she also knows where you can get moonshine. And so, and also Sylvia is an expert in another type of neutron experiment called neutron diffraction. In this case, it gives you atomistic detail, which is on the same kind of scale as what we can get from our simulations, but simulations can give you information about the dynamics, which her experiments couldn't. But together we studied lipids and proteins, or peptides in particular. And lipids are the molecules that make up cell membranes, and they have a hydrophobic tail, which is in the middle of the membrane, and then hydrophilic heads that like water on the interface. And so together, Sylvia's group and my group, we did really cool work looking at how water and different solvents and ions interact with proteins and helping them take different structural forms And also we looked at how the importance of hydration and solvation on lipid head groups, and we had a load of fun doing so. So these three people, Cecile, Jane, and Sylvia, our collaborations are so, like, this is the list of publications that have come. I'm not trying to brag, but just to show how important having great collaborations are to my career, because without that, my CV would look pretty unimpressive. So, yeah. Also, another thing I really love is studying lipid membranes. We've done lots of great work, or I think great work in this too. I'm not going to go through because I'm probably running a little late, but I just wanted to mention Peter Quinn. So Peter Quinn, he was a member of King's. Unfortunately, he lost a battle with cancer, but he is an amazing guy. So he was a small angle X-ray scattering expert, loved lipids. He was a biologist. At some point, he decided that he retired and he had loads of X-ray scattering data. He wanted to learn molecular dynamics so he could use it to complement and help him finish understanding his X-ray scattering. And then around the COVID time, he kind of officially joined my group, our group. And he would come to our meetings and online, we'd have him online. And he would bring all this biological content, and I learned so much. I think my students were in fear of him because he asked really hard questions, but it was great. And anyway, I miss Peter, and he was a great guy. So another great area of research which I've been working in is antimicrobial peptides, and this with James Mason, who's here as well. And antimicrobial peptides are small, positively charged molecules that are found in organisms and part of their innate immune system. And there's a lot of interest around them as potential antimicrobials because of all this the resistance that bacteria is making to antibiotics, which is all in the news. And we've done a lot of cool work where we combine all the experimental expertise that James and Mark Sutton at Public Health England have with some of the molecular dynamics stuff we can do to try to understand how structure and composition of those peptides affect how they kill bacteria. Again, we've had loads of great students working on this, starting with Sarah Beth, who was a master's student, and more recently, 3 students from South Africa. And then also even more recently is Maruna, a PhD student in my group, who's been looking into how in organisms, they have different mixtures of peptides, and some of them work, when combined, they kill bacteria better than them on their own, and this is called synergy. And so we're trying to understand how these peptides, why certain peptides are synergistic when others aren't. And so that's been a really fun and exciting project, which will continue. We've also done a lot of work in biomaterial interface, where the interface between materials and biology. We've done some work looking at how natural proteins and sugars can be used for lubrication, which was a really fun project. Matt did some work on a protein with fibronectin, and Muhammad Ali, not the boxer, but even a more amazing scientist, did some work on graphene therapeutics, if you use graphene as a therapeutic, and how the body might respond to that and the effect of it on the graphene, et cetera. In our group, I think we do a really cool job of not just analyzing our data in unique ways. And one thing that I really can take almost no credit for, but just again, having great people work for you, they do great things, or with you, I shouldn't say for, they work with me. But Paul Smith, Demi Pink, Rob, and now more recently, Maruna, they all have driven the application of machine learning in our group and in the field. So we use machine learning. We characterize our molecules with some kind of description of their conformation. We feed that into. We have loads. It's very high dimensional data. So we take that. We use machine learning to reduce the dimensionality to 2D, which you can kind of see this cloud of points up there. And then we use machine learning to cluster the points. And from that, then we can get we can understand different representative structures. And so we can kind of get order out of disorder. And then we can understand what these conformations are, where they're located in the systems we're interested in, and try to understand why it's important that they have certain confirmations in what they're doing. And this has provided us loads of insight that we otherwise would never had. Another thing which ties back to my PhD is that we've taken graph theory kind of approaches, which I learned from percolation and the algorithms that Bob used in his initial codes that I used. And we use this graph theory to understand how networks of molecules that are interacting with one another, whether it be when we're looking at how molecules aggregate, we can identify which ones are in aggregates together and which ones aren't. We can look at specific interactions and see which molecules are hydrogen bonded together, or maybe ring stacking interactions. And this again is, really has allowed us to get a lot of stuff that other groups probably haven't. And again, Paul, Demi, and Rob have all played an integral part in kind of integrating this into our research program. And these approaches then have led us to start to write our own software. But again, as I said, it's a lot easier to develop software when you're not the one doing it. So Paul wrote lipophilic, which is a code that is now used quite commonly by others to analyze molecular dynamics simulations of lipids. And then more recently, we've written a piece of code called PySoftK, which incorporates now PySoftWare, which was cleverly named by Rob. And this is those two, that PySoftK is really, so it has our ideas in it, but the father of it is Alejandro Santana Bonilla, who's a software research engineer in NMES, and without him, well, anyway, it would just be Fortran code. So thanks to him for all that. And and in doing this allows us to then interact with people outside of academia. And so one person who took an interest is Mark Storr, who is now a good friend and colleague and collaborator from AWE. And anyway, and so we're working with him now to try to get PySoftK into AWE and get some of the scientists there using it. So now I'm getting close to the end, so don't hook me off yet. But so going back to the philosophical question, is life cyclical? So in January 2024, Michigan won another national title. I celebrated at Passyunk Avenue, which is a great cheesesteak restaurant just across the river, with other Michigan alumni, and that was a great evening. That was just around the same time I submitted my application for the head of department position in engineering. And as Rachel said, I was very lucky to be appointed in this role and return to engineering. And then, of course, something else has happened recently again, which we're not so proud of. As far as future directions for my group, so I have a grant now from the Air Force Lab in America to study spider silk with my friend Greg in San Diego State. So that's something that's ongoing and I'm really looking forward to. I have a really great project with James Garnett from dentistry, and Maria's our PhD student working on it, looking at how proteins within Legionella bacteria that form biofilms, how they work. And of course, this bacteria is what's behind the disease, Legionnaires disease, so that's all really cool. And then I have a couple of really talented PhD students looking at different transmembrane proteins, one being iron transporter, and another, these proteins are involved in neurological disease. And so, so these things will be, and Shilan is a Chinese hip hop star. Kay Wong is her hip hop name. So, we're multitask talented in our group, so that's great. So what lessons have I learned from my career? I think it's great to be able to work with friends. So I would tell everyone, if you find people you like in this industry and you're trying to just work with them. It's loads of fun. It makes the beers after a nice paper that much more fun to have. I've been surrounded by amazing people in I've mentioned some, but there's so many, people here from the faculty who've been so supportive. Claire Cudby here is my department manager in engineering, and without her, she really runs the department. I'm just the one who says things every once in a while. But so lucky, so many people that support me, and I don't know. anyway, I'm just really blessed. And as I said, my giants are taller than everyone else's, and I've benefited from that, and it's not lost on me whatsoever. And I hope now I can start to be the giant for others. Don't ever stop learning, because then if you're not learning, you're probably dead. And I think what I did, I was the head for the engineering department when they had their inaugural lectures this year. And the two people who were recognized then were people like me who had a technique that then they applied to a range of things. And I don't know, and then there's types of academics who have one field of science and they are really expert in that. And I think both ways work. And so I think just, for those aspiring to be here one day, just figure out the way you want to do it, and it'll be fun. So I just these are just group photos. I didn't get to talk about everyone, because again, I only have so much time, but these are my group-based members from various times, and different lengths of beards for me, and different amounts of food I'd eaten in the past 6 months before. But anyway, thanks to all of them, because obviously without them I wouldn't be here, and I wouldn't have had as much fun. And then there's all everyone else, people from engineering, physics, outside of work. So lucky. I'm so lucky. So thanks a lot, and yeah, thanks for giving me this opportunity.
So thank you very much, Chris. For those of you who don't know who I am, my name is Mark Green. I'm a professor in the physics department, and I'm a long-standing friend and colleague of Chris's. And it's a real pleasure tonight just to give a vote of thanks for his inaugural lecture. The whole point of an inaugural lecture is to celebrate, recognize, and hopefully explain better an individual's work and achievements. And today we've been fortunate enough to listen to 2 inaugural lectures from 2 outstanding professors. But my job is to briefly touch on Chris's contributions, not only to the scientific community, but to King's in general. First of all, I'd like to congratulate Chris on a fantastic lecture. And I'm not at all surprised that Chris can actually get across what he does in such a simple way. In fact, one of Chris's great strengths is to give science a very human and very accessible face. To give a very specific example, Chris and I worked on a project together during the COVID period. We were looking at developing new particles to detect the virus. So we often sat in his office with Rob, the postdoc who's here tonight, and Chris explained the finer points of the project to me. And I understood it. And then I went back to my office, and then I realized I haven't got a clue what percolation theory is. I have no idea. And this is a sign of a good teacher and a great scientist, that he can make you understand a very complex, very difficult discipline very quickly. Only if you realize later on your own failings, actually, you're not as good as he is. I'm sure I'm not the only person who's benefited from collaborating with Chris. As you've seen through some of his slides, Chris has worked not only with numerous departments and faculties within King's, but also universities, research institutes, and industrial partners across the world, which just highlights how successful a scientist he is. So far, he has published over 130 papers with collaborators across all disciplines. Now, one of my favorite stories about Chris actually revolves around one of my own publications. Nature Nanotechnology 2013, chapter 12, pages 365 to 375, PDF 7 line. But when I got this paper, a high impact paper in 2013, I thought Chris might like to read it. So I sellotaped it to his office door. And when Chris moved offices, he actually took it off his office door and put it on his new office door. Now, that was there for 10 years. Now, when Chris published a better paper in 2021, I can't remember the reference, he didn't return the gesture. He just passed up this opportunity for revenge and one-upmanship. So I wouldn't have done that. He's clearly the better man. Like I said, 10 years that stayed on his office door. So this speaks volumes for the kind of guy that Chris is. He's quite willing to share the spotlight, whilst others take the glory. He has quite impressively made headway in computational material science since he's been at King's in 2007. Now, the high respect that he's held in is evidenced today by so many people turning up to listen to him talk. People have come across from the States, people have come across from the world, friends and family alike. And it's this strength of character that led Chris to being the interim head of department in the physics department during what is arguably one of the toughest periods in living academic history during the COVID era. And it's this strong leadership that absolutely stands out during his tenure. Now, I'm going to wrap up in a minute. Chris has treated us to an insight into his research and shared with us some of his achievements, but there's more to him than academic excellence. He is often sought out as a calm voice of reason within the faculty and always gives clear, level-headed advice. And personally, I find his counsel invaluable. I think I should stop there. I just want to say thanks again to Chris, thanks to Jean. Congratulations on the lectures and well done. Thank you.
Thank you. So thank you again to the speakers and all the votes of thanks, which have been tremendous. Just a few final closing words. I know I'm between you and the drinks and the snacks, so I won't be long. Fascinating science, I think you'll all agree. I think we've learned lots, and we've also seen that passion and joy and excitement from the professors, which has been wonderful. I said a common theme of beer, and yes, we saw the common theme of beer. But the other common theme that really struck me was the importance of mentorship, the importance of collaboration. Chris talked about standing on the shoulders of very tall giants. Jean talked about how instrumental his time was as a PhD and postdoc, developing those ways of thinking and the mentors that he had. To me, one of the things that makes the Department of Physics and Engineering, makes the faculty, makes the college such a great place to be is the people. That's always what enables great stuff to happen and what supports us in our work. And I think it's worth reflecting on the roles of professors in that. These are our leaders in the institution, and we really want giants like John and Chris are, who provide that support and mentorship and encouragement and inspiration to our students, undergraduate, postgraduate students, our early career researchers, our postdocs, our junior members of staff. And so I just want to hold them up and thank them, and let's just applaud them once more, I think. And I hold you back no longer. Do join us for reception for drinks.